Hello and welcome to today's lesson on neutron emission. In today's lesson, we will understand the properties and factors that cause neutron emission. We will then learn how to write the nuclear equation for neutron decay. So far, we have explored various types of radiation, including alpha, beta, and gamma radiation, along with their associated nuclear equations. Building on this foundation, we can now introduce neutron radiation. By studying neutron emission, we gain deeper insights into the transformative nature of nuclear processes. Let's get started. Let us start by recapping what neutrons are. Neutrons are neutral subatomic particles found in the nucleus of atoms alongside protons. Neutrons have a similar mass to that of a proton, but unlike protons, neutrons carry no electric charge. When an unstable nucleus undergoes neutron emission, it ejects one of its neutrons. This process decreases the mass number, the total number of protons and neutrons, by 1 because the nucleus loses a neutron. However, since the number of protons is unaffected, the atomic number remains unchanged. Neutron emission typically occurs in neutron-rich nuclei. These nuclei have an excess number of neutrons compared to protons, which can lead to instability. By emitting a neutron, the nucleus adjusts its balance between protons and neutrons, aiming to achieve greater stability. Neutron emission is less common than other types of decay, such as alpha or beta decay, but is an essential process in specific contexts, particularly in nuclear reactors and fission reactions, which we will explore more later in this unit. To illustrate neutron emission more concretely, let's look at an example to see how this process is represented in a nuclear equation. Consider the example of beryllium-7 undergoing neutron emission. We start with beryllium-7. This isotope has a mass number of 7, which is the total number of protons and neutrons, and an atomic number of 4, indicating it has 4 protons. During neutron emission, the beryllium-7 nucleus emits a neutron. A neutron has a mass number of 1 and an atomic number of 0. Next, we consider the mass and atomic number conservation. The initial mass number of beryllium-7 is 7. When a neutron, which has a mass number of 1, is emitted, the remaining nucleus has a mass number of 7 minus 1, which is 6. The atomic number remains unchanged at 4 because the emitted neutron has an atomic number of 0. From this, we can identify the new nucleus. Since the atomic number remains unchanged, the element remains as beryllium. The new nucleus formed has a mass number of 6, so the new nucleus is beryllium-6. Thus, the balanced nuclear equation for the decay of beryllium-7 via neutron emission is B7 becomes B6 plus a neutron. Let's try a couple of problems to solidify our knowledge. Here, we need to write the neutron emission equation for lithium-8. We can identify the initial nucleus and its properties as lithium-8 with an atomic number of 3. When we determine the changes after emission, we know that when lithium-8 emits a neutron, the mass number decreases by 1 from 8 to 7. However, the atomic number remains the same, and so is still 3. From this, we can identify the new nucleus. The element with an atomic number of 3 is still lithium, so the new nucleus is lithium-7. Now we can write the nuclear equation, which is lithium-8 becomes lithium-7 and a neutron. Our final problem is to write the neutron emission equation for boron-12. As always, we identify the initial nucleus and its properties, which in this case is boron-12 with an atomic number of 5. We know that when the boron isotope emits a neutron, the mass number decreases by 1 from 12 to 11, but the atomic number remains the same at 5. We then identify the new element, but the element with an atomic number of 5 is still boron. Therefore, the new nucleus is boron-11. We can now write the nuclear equation, which is B12 becomes B11 and a neutron. In today's lesson, we delved into the properties of neutron radiation and its role in the process of neutron emission. We learned that neutron emission involves the release of a neutron from an unstable, neutron-rich nucleus, leading to a decrease in the mass number by 1 while the atomic number remains unchanged. We illustrated this concept by examining the decay of boron-12 into boron-11 with the emission of a neutron. By practicing writing nuclear equations, we saw how mass and atomic numbers are conserved. Understanding neutron emission provides significant insights into nuclear stability and the complex mechanisms of radioactive decay, preparing us for more advanced topics like nuclear fission.